Hello everyone and welcome to today's webinar in our prestigious school. Today we have a special guest, a fellow Algerian nanoscientist, Professor Maaza. On behalf of the school, the staff, the students, I dearly welcome you here with us today.
Thank you. Thanks a lot, Program Director. Allow me please to share my screen.
Professor Maaza was born in Bosch Bouarerij, studied and graduated from the University of Oran in the field of physics. He then went on to explore the mysteries of light, where he got a master's degree in photonics at the University of Pierre and Marie Curie. He then got a PhD in the same institute and then went on to seek knowledge from various countries, including Germany, Italy, and Austria. After that, he decided to come back to his home continent, specifically to South Africa, where he became the UNESCO Africa Chair in Nanoscience and Nanotechnology. In his career, Professor Maaza got many valuable rewards that reflect the importance of his achievements, some of which are the Galileo Galilei Award by the ICO, which is the International Committee of Optics, and the Algerian Scientist of the Year, which was given to him this year by President Abdelmajid Tebboune. Welcome again, Professor Maaza. Thank you for accepting our invite, and please take it from here.
Thank you so much, Program Director. First of all, allow me to express my gratitude to all organizing committee who invited us to share with you this endeavor. First of all, second, I wish really to express my gratitude to all senior and junior colleagues and fellows who are attending this webinar. My webinar today is titled Nanosciences for Sustainable Development Goals and Science Benefiting the Society. This this webinar is given within the framework of the UNESCO, UNISA, Itamba Labs, NRF, Africa Chair in Nanosciences and Nanotechnology. This UNESCO Chair is a trilateral partnership between the UNESCO plus Fontenoy in Paris, the University of South Africa in Pretoria, and Itamba Labs NRF in the Western Cape here in South Africa. The outline of my talk, in effect, consists of three major parts. I will introduce who is, in a succinct, concise way, who is the U2ACN2. Then I will embark on some generalities on nano for a general public understanding. Then I will go and share with you a number of applications of nano materials in a number of fields, being it health, being it energy, being it agriculture, and being it the water. The U2ACN2 stands for the UNESCO UNISA Africa Chair in Nanosciences and Nanotechnology. It is based in South Africa. It has two nodes, one in what we call in the Gauteng region or the Gauteng province, that is Pretoria and Johannesburg, at the UNISA Science Campus. The other one, it's in the Western Cape, not far from Cape Town, at the Itamba Labs. And the mission and the vision of the UNESCO Chair is to further and cement and to be the voice of nanosciences and nanotechnologies within the African continent. And yet it is headquartered in South Africa. It has trained and it is training and it will train a large cohort from the African continent, the different corners of the African continent and beyond, in particular the Middle East and the South Asia and the Middle East, as well as Latin America. But our footprint is in Africa. In that regard, the number of fellows have been trained, being it students, postgrad, MScs, PhDs, as well as early career scientists and senior scientists. And these fellows, following their training at the UNESCO Chair headquarters, they go back to their home countries where they implement nano activities. And as you can see, specifically in the case of Algeria, we were working extensively with the CDTA in the Sidi Hassan in Algiers, not far from the center of Algiers, as well as le Centre de Développement des Technologies Avancées, as well as the University of Tlemcen, with whom we have quite a number of robust cooperation and synergies. And of course, a number of other countries where we have trained the fellows, and they went back and created, some of them have created outstandingly robust centers, such as the CREATES in Tanzania or the CBBR in Mauritius, and so on and so on. We have been also very robust in cementing nano activities in the northern of Africa, that is Egypt, Tunisia, and Morocco, and Algeria, of course. Our vision within the UNESCO chair, it is not only to train students to acquire a diploma, and also to allow the early career scientists and senior scientists to have to embark in a large mobility within the continent, sharing our research facilities and sharing our limited fundings and so on, but to optimize on that, but certainly also to encircle in the spirit of the early career scientists as well as the postgrads, MScs and PhDs, the spirit of entrepreneurship and innovation, and embarking in addition of knowledge production, embarking in science for the society and developing solution for the problems of the society, being it the energy, health, water, and the agri sector. And the idea is to have multi-skilled fellows who are capable to, how can I say, use their know-how acquired in finding solution to the society problems. So, as I mentioned, since the beginning of the chair, as you can see, quite a large cohort of fellows have been trained from different parts of the continent, as you can see, including Libya and Rwanda during that time. This fellow in the meantime, and also not only limiting ourselves to MScs and PhDs, but also to early career and senior scientists, allowing them to come to South Africa from their home country to use our facilities and to use the facilities that we have access from overseas, such as synchrotrons, such as ultra high power lasers sources, including nuclear reactors facilities. And also in our program, there is a strict respect of the gender equity, whereby 50% of our fellows, being it postgrads, MScs, PhDs, or early career scientists, or senior scientists, 50% of them are females and 50% of them are males. Just to give you an idea about how the quality of the research that we publish, as you can see here, this is the citations of our publications with the affiliation of the UNESCO chair. As you can see, they are increasing within the years, and last year we reached we went above 5,000. These citations by colleagues from China, India, Russia, Australia, or Europe, the Americas, Latin or North America, does reflect the quality of the research outputs that we are carrying out within the framework of the UNESCO chair. So which means not only we are training fellows, but we are producing research of a high quality. Therefore, it is cited by scientists in China, in Russia, in Europe, and in the Americas. Again, how can I say, while it's extremely important to embark in R&D translations, the field of nanosciences and nanotechnology is a really pivotal, and it can be used as a platform to embark in a very competitive forefront type science and technology. And the specificity of the field of nano is sometimes it requires a massive investment, but sometimes medium or nearly minute amount of investment to come in. And why? Because the field of nanosciences and nanotechnologies is size dependent. So I will not, please excuse me to use this image. I am very well aware that you know what is a nanometer. If you take 1 meter, you divide it by 1,000, it gives you a millimeter. If you take that millimeter, you divide it by 1,000, it gives you micrometer. And if you divide the micrometer that was in the last century, that was the size that we were able to build, to make, to fabricate, and to be able to observe. But if you take that micrometer, you divide it by 1,000, it gives you a nanometer. Now we are capable to manipulate matter at that level and to observe it at that level. And therefore, it is extremely sound and easy to access this technology with a minute amount of investment. Size can be controlled. As much as we are speaking about the size, I want you colleagues and fellows, senior and junior and students to understand what does it mean size. If you take the image that we have always seen in our classrooms, in our administration and so on, that word map is wrong. It is false. ألف false. غلطة كبيرة. علاش? Because if you take the word map as is, as the one that we use, this is the Mercator projection. It shows nearly that the size of Africa is the size of Canada or the Groenland, which is incorrect, colleagues. It's incorrect. This projection of Mercator was used to, how can I say, was plotted then by the colonizers in the past to put Europe as the center of the world, and by doing as such, the sizes are shrinked in the equator, and if you are far from the equator, the sizes are elongated. So the distance from here, from Dakar to the Horn of Africa, that is Somali, it seems that it is smaller than the distance from St. Petersburg to the east part of Russia, which is completely wrong. This distance here is smaller than the distance between Senegal and the Horn of Africa, and in such a way that the true size of Africa is the size of the US plus Nebraska, the size of China, the size of India, the size of all East Europe, plus the size of all West Europe, plus Japan, as well as in the UK, in Madagascar. So, colleagues and fellows, you do understand that Africa is an extremely large continent. In addition to its size, which is extremely big, Africa is the youngest continent in the world. More than 73% of its population is less than 18 years old. Therefore, in addition to that, 10 youngest countries are in the world are in Africa, and the youngest country in the world is in Africa, and it's not far from the south of Algeria. In effect, I leave you guessing it. Is it Niger? Is it Mali? So it's up to you to go to do your homework. The point is, this large and massive youth coming in has to be trained. And if it is trained correctly, and if this youth embarks in R&D translations, in addition to knowledge production and educating themselves, they could be the Steve Jobs, they could be the Marie Curie, they could be Einsteins of the future, and there is no limit to the sky. So, colleagues, and in particular the youngsters, you do see that the size matter. Africa is extremely large relatively to a number of other continent and country, and it's the, how can I say, it is extremely rich, not because the minerals on the ground, but the youth of it. And you are the ones. Please, you have to consider that you have to be convinced that you will be playing a huge role in the future. Well, what was the source of pushing the nano? Why the nano has been pushed extensively? The nano has been pushed extensively because of this. When I was a student, I was using this IBM discs, which were around 20, if not 30 centimeter along this side, and it is nearly square of 30 centimeter, and with a thickness of around half millimeter. But these discs that I was using, and a number of the senior colleagues in the audience were using to store their information, was able only to store 1 page, even not a half a page of handwriting. While currently we have USBs of a terabyte, and that, how can I say, and this terabyte can host thousands and thousands of music, MP3, as well as movies. You would say, how it come that before the size was big and the storage capacity was low, and now we have small storage compounds, and we can store more information. The difference is that before, in that large IBM disk, the information, the 0 and the 1 bytes, they were stored on millimeter size area, or sub-millimeter. While here, the information in the terabyte USB, the 0 or the 1 information is stored on a nanometer scale. And you would understand that where the community internationally is working on possibility of storing the 0 and the 1 on a sub-nano. And even not only the 0 and the 1, but their combination, so the qubits, so that on a smaller area, therefore, the capacity and the speed of storage will be extremely far advanced. So that is, colleagues, it was the ICT who has driven like a hell the field of nanosciences and nanotechnology. You would understand, colleagues, that from historical point of view, we are not the first ones. We were not the first ones to come in. Just to remind you that, fellows, that the term of nano was coined by Norio Taniguchi, a Japanese scientist. And it was Richard Feynman, the famous physicist, theoretician, who predicted that in the year of 2000, we will be able to manipulate matter at the nanoscale, and we will be able to have devices at the nanoscale. But before them, colleagues, the Romans were able to make nano without paying attention. They were mixing gold salts with a glass, in a glass, during the glass formation, and in effect, what they were doing, that gold salt mixed with the number of precursors for the fabrication of the glass. In effect, the gold salt decomposes and forms nanoparticles of gold. And depending on their size, if they are small or large, they have different plasmonic optical activity, and therefore they give different colors: green, blue, red, and so on. But before, colleagues, before the Romans, well, Mother Nature has been able to fabricate nanoparticles. In that regard, specifically if you take the bacteria, remember colleagues, bacteria is the first living species which was created on Earth, as much as the science tells us. And this magnetostatic bacteria, colleagues, what it does, uh, it fabricates iron sulfide or iron oxide nanoplots inside of its body. And these small magnetic blocks of iron sulfide or iron oxide in effect they orient themselves according to the magnetic field of Earth. And therefore it's only in the 80s that we were able to explain more or less the formation of these nanoplots in a magnetostatic bacteria. So colleagues, you would understand that the bacteria, when it produces these blocks, building blocks here of iron sulfide or iron oxide, it does it in an extremely very cost-effective energy-wise. It uses a minute amount of energy to fabricate them. So we have a bio-natural factory of nanomaterials. And now, colleagues, what is the specificity of a nanomaterial? A nanomaterial, if you take a sphere, colleagues, and why the properties do change according to the size. Why they do change depending on the size. If you take, let's say, imagine that you take a spherical nanoparticle. If you take spherical nanoparticles, you will find out that the atom, if I take an atom inside the particle, it has a 3D symmetry. An atom will see 6 atoms, right, left, from the different directions. But if you take a particle on the surface, it will feel, it will not see 6 neighbors, but less numbers. Therefore, the 3D symmetry is broken. And in addition to that, if the 3D symmetry is broken, atoms will behave differently from the bulk, because the bulk is a 3D symmetry. Here, the 3D symmetry is broken. So any property, thermodynamic, electrical, whatever, name it, depending on the 3D symmetry, is broken, will not be the same. In addition to that, the surface of the atoms of the surface will vibrate differently, and therefore their phonon contributions will be different. And when you speak about the phonon distribution, that means you are speaking about the thermal conductivity of a material. The thermal conductivity of a nanomaterial is different from the thermal conductivity of a bulk material. In addition to that, colleagues, when you take a free electron, let's say we take gold nanoparticles. Gold is metallic or silver is metallic. If you take a metallic nanoparticles, you do remember that you have free electrons in a metal. These free electrons will not be able to move freely in the on a long distances. No, that free electrons or free carrier will be confined in a space, the space of the volume given to it by limited size of the nanoparticle, and therefore the electron is confined, and therefore the electron would not behave classically but quantum mechanically, and therefore it will behave as a wave, not as a particle. And if it behaves as a wave and not a particle, it will be governed by quantum mechanic principles and not classical property regulations. and therefore the optical properties will be different. And you would see that in effect, gold, when it is big, it's yellow. When it is small, when it's nano, it can change color: green, blue, red, and so on and so on. In addition, colleagues, what is extremely important in a number of applications is that the number of atoms on the surface of a nanomaterial can be higher or equivalent to what, to the number of atoms inside. If it is the case, therefore the properties of the nanomaterial is governed by the atom surface, and the surface of located in the atoms located in the surface, and not those who are inside as in the bulk. And just to give you an idea, colleagues and fellows, is that when you take a cube, a small cube of a gold, let's say, for example, initially that cube has 6 sides, 6 faces. If you cut it in two, you will create 2 additional faces. If you can continue cutting it, each time that you are cutting it, you will be creating new surfaces. And by creating new surfaces, you are enhancing by far the surface to volume ratio. And by doing such, you are making the material extremely, very, very active. Instead of sending a cube of 1 millimeter size of a gold to kill an a cancer cell on the skin, it's better. It will be easy to how can I say, to use just a small amount of nanoparticles of gold to kill the same cell. Just to give you an idea in terms of surface to volume, please remember this number: 1 kilogram of particles of 1 millimeter cube has the same surface as 1 milligram of particles of 1 nanometer cube. In the exhaust in the cars that we use platinum. Platinum is extremely expensive. Therefore, in the automotive industry, they will not use large particles of platinum, but rather small particles of platinum. They gain in cost, and also they gain in surface. So therefore, the amount of platinum that the automotive industry will be putting in the exhaust to decompose the harmful gases coming from the exhaust for platinum will be smaller, and therefore the cost of the car will be reduced. Again, colleagues, as I mentioned, if gold is yellow in bulk, depending on its size, on its shape, when you go to the field of to the scale of nano, its color changes because its optical properties are governed by quantum mechanics and not the classical physics anymore. And the same applies for silver whenever you play on a shape, colleagues. So size and shapes are extremely important, and that is why it's easy to enter the scene of nanotechnologies. Here, colleagues, just to give you an idea about the melting temperature, how the size affects the melting temperature, which is the thermodynamic major property of materials. That is the melting temperature of gold nanoparticles, depending on their size. As you can see, smaller is the particle. If the gold melts around 1300 degrees Kelvin at the nanometer scale, if your particles are extremely small, they melt at room temperature nearly. And also, in effect, without paying attention, the green color of this screen, flat screen laptop, and the flat screens of your cell phones, the green colors, the blue, the red color, the yellow color that you see, in effect, it's not a rare earth, but it's zinc sulfide with different sizes. because the materials at the nanoscale, their band gap is not fixed. It's not an intrinsic value of the material as in the case of a bulk, but it's a size dependent. Smaller is the size, higher is the band gap, so higher is the excitation and higher is the luminescence, lower is the luminescence, colleagues. So you are using nano in your cell phones without paying attention, without knowing it. So the band gap, colleagues, that you will see in solid state, or those who have seen the band gap of materials for the bulk, it's an intrinsic value, but for at the nanoscale, the same material, but at the nanoscale, it's size dependent. And colleagues, also the properties of materials at the nanoscale depend not only on their size but on their shape. Here it is zinc oxide. This is zinc oxide. It's the cream that you use when you go to the beach or when you go to the mountain and you want to protect your skin from the UV radiation. You use a zinc oxide formulation. That zinc oxide has a specific property. It stops the UV in the form of a bulk, as well as in a form of nano. But in the form of nano has different shapes, are geared towards different properties, being it electronic, being it optical, being it magnetic, and so on and so on. You will find the nano systems in different ways. You will find them in a form of a nano powder consisting of nanoparticles. You will find them also in a form of a nanocomposite or in a form of shape anisotropy nanomaterials like carbon nanotubes, or you can find them in a form of thin films. As much as one of the sizes of your material in one of the three dimensions is less than 100 nanometer, it is called a nano material. This is more or less schematic description. The real description here is a nano silica, nano squared of palladium, nano triangular nanoparticles of silver, cylindrical type nanoparticles of gold. Here are C60 carbon nanotubes, extremely long. Here are nano ribbons of zinc oxide, as well. Here there are multi-layered systems for X-ray optics. And just to more or less close this chapter of nano, colleagues, just to get a clear idea where we are, where we were, where we are, and where we are going, is that in the 17, where the human society was dominated by the coal industry. In the 50s and the 60s, mainly the 50s, it was our society was driven by nuclear era. In the 60s, our society was driven by the semiconductor technology era. In the 70s, it was with the biotech. In the 80s, it's ICT, and in the 90s, it was nano. But the combination of nano, ICT, and biotech, as well as semiconductor, is gearing us towards artificial intelligence and ultra fast calculations, as well as a massive data treatment, in addition to a large amount of data storage capacities. You would understand that all of these coming technologies or upcoming technologies will be based on materials at the nanoscale. It is only the sub-nanoscale that would able to move towards Moore's law and to be able to respond to the requirement of heat removal from the data centers and the high storage and high calculation that artificial intelligence requires. Colleagues, I will not. I just want to give you also an idea about how much investment is, how can I say, is spent in the field of nanosciences and technology. As you can see, these are per countries. You would see we have stopped around 2005, 15, but we see that the funding in US millions here. We are at the level of billions now. And well, a number of countries are investing massively in it, and I do commend the government of Algeria in creating this school of yours, because it is a must. It is really a must in that regard. And the field of nanosciences and technology is multidisciplinary but material based. It can impact different disciplines, if not each and all the disciplines. The research that I would like to share with you is in relation to the Sustainable Development Goals. If you don't know what does it mean, Sustainable Development Goals, please forgive me in that regard to insist that if we contribute, the United Nations came with around the 17 Sustainable Development Goals. If each of us will contribute directly or indirectly to one of them, we will make our Mother Earth we revive it again. So I will share with you some of the technologies that we developed within the UNESCO chair, related to the health, related to water, and related to energy, as well as climate actions. A typical case is that let me jump this once and I will go straight forward to the applications. Here is some applications in the health sector that fellows of the chair have been able to come with. I would just to mention that in fact, in addition to the United Nations Sustainable Development Goals, different institutions now, high education institutions, research centers, have embarked in their policies in terms of priorities in the field related to the Sustainable Development Goals. In our case at UNISA, the Vice Chancellor has came with a number of priorities that is called the Vice Chancellor Catalytic Niche Area. So even the responsibility is coming down from the top organization, international, to president, rectors, and directors of institutions such, and hopefully your school will also embark in that regard. The first example that I would like to share with you is related to skin cancer melanoma. It happened that in this, I would like to share with you more or less who has done the job. It's not me. Those who have done the job are fellow from South Africa, from Botswana, from Egypt, and from Iran, as well as senior colleagues from Pakistan, Belgium, and India. One of the major problems that we face in Southern Africa, not only in South Africa, but the full Southern Africa region, and it is the equivalent also in the north, is a high direct normal incidence, solar incidence, and therefore it is above 220 watt per meter square, and therefore the communities do suffer from skin cancer melanoma, which is induced by the UV radiation. UV radiation is around 5% of the normal solar radiation emission spectrum. Therefore, it affects when you have high DNI, you have to protect the skin, otherwise you have the skin cancer melanoma. And it happened there is a community in southern hemisphere, they call it the Khoisan, and this black community, Khoisan, seems not suffering from this skin cancer melanoma. Why? Because they use this herb here, which is the equivalent of a sheikh in Algeria, Artemisia afra. It is the equivalent, not exactly the same, but equivalent. So they chew this plant and they mix this the natural extract of this plant with the goat milk to make a formulation, and they use it on their skin. So what we have done is that the fellows that I have shared with you, these fellows, they took the natural extract of this plant, and the natural extract of this plant, uh, uh, they mixed it with the nanoceria, cerium oxide at the nanoscale, as you can see here. They have used this to biosynthesize this cerium oxide, sorry, and by using, how can I say, uh, making or bioengineering these nanoparticles of cerium oxide, they tested the UV, how much it stops the UVA, the UVB, and the UVC, which is a part which consists of the UV spectrum region. Well, colleagues and fellows, this is the stopping power of this cerium oxide bioengineered with this natural extract of this plant. As you can see, it is quite large. It stops the UVA, UVA1, the UVA2, UVB, and UVC, while the ones that you find in the commerce, being it organic or inorganic, they have a very sound, significant stopping power, but it's limited in the spectrum. While this one, the cerium oxide, synthesized by this one, by the fellows that I have shared with you, is quite large, and it stops all this radiation. Therefore, it will not affect the hypodermis, and so on. It stopped nearly at the skin of the surface itself. So it stops, how can I say, the epidermis, the dermis, as well as the hypodermis from this harmful UV radiation. And it was published in one of the major top journals in Nature Scientific Report. Also, this, how can I say, not only this cerium oxide bioengineered using natural extract of Hoodia gordoni, which is the equivalent of Artemisia afra, that is the equivalent of Sheikh in Algeria. It stops the UV extensively, as you can see, but also it has a low ROS. That means it will not affect the DNA. So even at a high concentration, it will not affect the DNA. So this cerium oxide formulation is very effective in stopping the UV without harming the DNA, and therefore mild for in terms of applications. The second case that I would like to share with you also is something also borrowed from indigenous knowledge. احنا نقولوا في الجزائر سافوار تراديسيونيل. من تكون في الغابه أو في الجبل ولا ما كانش دكتور، تروح عند جدك ولا جداتك ولا ناس كبار تقول لهم راني مريض، راه عندي هاد لا بليسيور هادي، ولا عندي هاد الحبه هادي، ولا والجرح، تعطوني حاجه، يعطي يقول لك روح تجيب هذاك لا بلونت ودير الفورميلاسيون. سي اكزاكتومون لا ميم شوز ici. So in terms of indigenous knowledge based, they have used also an indigenous knowledge to synthesize very effective and cost-effective traditional antibacterial by a fellow from Sudan, from South Africa, Sudan, Botswana, and Iran, as well as Iran. There is a physicist and a modeling expert, chemist, material scientist, and physicist and material scientists. I will not go through the details here, but what is sure is that this community that we call a Himba, they live in the north of Namibia and in the south of Angola. This community do not shower at all because water is scarce. ما يغسلوش رواحهم خلاص. علاش الماء ما كانش بزاف الماء في هذيك لا ريجيون. واش يديروا يحكموا هاد واحد لا غوش it's a rock, it's an iron oxide rock, and that they crush to make a powder, and they mix it with goat milk to make a formulation, and they coat all their body, all parts of their body, including their hairs, with this formulation. And this formulation is red, what they call it red ochre. It happens that this rock that they are using, if you go to electron microscopy, you would see that it's nanoscaled. It's a lamellar nanoscaled system. As you can see, the size here is 5 nanometer. So it's nanoscaled, and better than that, when you do the optical properties, when you investigate the optical properties of this material or this formulation of a red ochre, you will see that it stops the UV not at 90% but above 95%. In addition to that, it protects them from the skin cancer melanoma somehow, but it reflects more than 50% in the near infrared. What does it mean? That means that it protects their skin from overheating and overburn, and therefore that is why they do not suffer any overburn, because la température في البلاصه وين فيها هاد الناس هادو توصل ل 56 degree Celsius. So it can be extremely overburning, but they do not suffer from it. But better than that, colleagues, is that when you test the antibacterial properties of this red ochre, you will find out against the E. coli and the Staphylococcus aureus. You see these ones, the first ones are the streptomycin, which is used as a reference, and this red ochre used by the Himba people at a certain concentration. It is even at a lower concentration is effective. It has an antibacterial activity. At a higher concentration, it can be extremely significant. And what does it mean? That means it explains why why this community does not suffer from any bacterial infection, that yet they do not shower the way that we shower. They don't use water because water is only for drinking, not for shower. So colleagues, you would see that in effect this nanomaterial red ochre that they use also is very effective as an antibacterial, but better than the colleagues. As you can see, it was also published by an MSc students as a first author in this prestigious journal of Nature Scientific Report. The other case that I would like to share with you, colleagues, is that the cost, the fertilizers. All of us worldwide, we have seen the prices of food rocketing. The price of food rocketing, it's due to, of course, to the inflation, but also it's due to the fact that any agri-farming would need to use fertilizers. And these fertilizers do come mainly from some countries, that is Ukraine and Russia. But these fertilizers for the plant, not for the soil, do come from these countries, and these countries are in war, and therefore the market, the supply is affected, and therefore the prices have gone up. And therefore it is necessary to produce fertilizers at a home place. A number of even for the local farmers, even if it's a small farming unit, it is necessary to use local produced fertilizers. And I would like to share with you, colleagues, those who came with a solution. This is a fellow from from Botswana, from the Democratic Republic of Congo, PhDs, postdoc from Egypt, and a postdoc from Botswana. So these fellows came with producing a nano chemical fertilizer that is, but not an organic one. The organic one do require a specific chemistry and so on, while the chemical fertilizers are not food for the soil, but food for the plant, and these are carbonates, magneta, and other compounds. So here these fellows have produced the calcium carbonate and other number of carbonate. I will escape these ones. They have made and bioengineered nanoscaled nanotubes type of calcium carbonate, as you can see. And these ones, colleagues, have been tested on tomato plants. Why tomato? Because tomato grow fast. So you can test easily to see how long time the plant reached the flowering and how long time the plant has reached the food production. And as you can see, this one without any fertilizer, this with a small amount, with an average amount, with a larger amount, with a larger amount, lower than threshold toxicity. As you can see, here is the tomato without, the tomato with small amount, average amount, a large amount, and very large amount. So you can see, and the nutritive value of it was checked. It is the same. In addition to that, is that as you can see, the size is bigger, so which means that this fertilizer is very effective indeed. Again, these results were reported in this prestigious journal Nature Scientific Report by these students. In terms of water, colleagues, you know that water is a really major problem in a number of countries, not limited to some countries, but in all. Here is, I would like to share with you a nano solution or nanotechnology within which was involving a PhD from Senegal, a postdoc from South Africa or Botswana, and from Egypt, Iran, and an engineer. Here is an engineer. Here is modeling, molecular dynamic and density functional theory, computational expertise. Here is material science. Here is a chemistry, physics, chemistry, and material science. And these fellows came to address a problem. This problem is the following: is the water scarcity all over the African continent. All over. You would see that the blue cyan bars do correspond to the water availability in 1990. 1990. The dark bars are the water availability this year, 2025. This was predicted in 1990 by the United Nations, by the global, the International Water Council, and so on and so on. You would see that nearly all African countries are under vulnerability. What does it mean under vulnerability? That means some communities will not be able to have water to wash. But the most dangerous one is the number of countries will be under scarcity, which means that some communities will not have a possibility to or access to drinkable water. That's the point. Some people will not be able to drink water. And north of Africa, as you can see, is in the red, in the scarcity also. So is South Africa and the region of Ethiopia, and so on and so on. Therefore, it is necessary for us to decontaminate the water that we are using when we shower, when we go to the toilets, and so on and so on. That water has to be treated, and specifically the water used in the agri sector, using pesticides. Agri sector uses a huge amount of water And if, of course, you may say we have to embark in using underground water, but what about the future generations? We cannot deplete the water resources without thinking about the upcoming generations. It's morally anyway. The fellows have embarked in developing a photocatalyst which is active in the visible range or near infrared. By doing such, or they have embarked of using the standard photocatalyst that everybody uses, that is titanium oxide. But but in effect, the modeling, this TiO2 is very effective, yes, but it is active only in the UV region. And remember, the UV region in the solar cell, in the solar spectrum, is only 5%, not much, not much. So if you want to disinfect water, you have to use artificially generated UV, and this is extremely expensive, extremely expensive, and it uses mercury, which is one of the most dirtiest elements with arsenic. So what these fellows have done, in particular these two fellows here, the modeling one from Iran, and Dr. Shora, the engineer, also from Iran, they came with the modeling, as well as Razia Murad from Iran. They showed that in effect, if we create defects on the surface of the TiO2, we will be able to make it active. So the TiO2, which is generally speaking a white powder, if you create defects on the surface of these nanoparticles of titanium, they are black. If they are black, they will absorb light. They will be active not only in the UV but in the visible as well as in the near infrared. And that's exactly, colleagues, what was obtained. Here you have nanoparticles of nanoplatelets of TiO2, and as you can see, it's black, the bulk, annealing 100 black, 200 it's changed a little bit phase transition, 250 black, 350 black, 350 black, and 400 black. And this one, the 400 one, when you anneal further, you you go for phase transition. We are interested by the 400 one because it is that one which is extremely very good. You do ESR to see, to confirm and to validate the creation of defects, but I will really escape this. It's purely fundamental. What is sure is that black TiO2, by opposite to the white TiO2 that we use in a paint and we use to start, how can I say, in our sunscreens when you go to the beach and so on, the black TiO2 absorbs in the visible, the UV, the visible, and the near infrared, and therefore it is active in the near infrared and the visible. Therefore, we can use solar energy to activate it. Here, what we use to check if it can decompose the pesticides from the agri sector, the water contaminated with the pesticides in the agri sector, what we do, we take what we call methylene blue, and methylene blue, if you decompose it, you will be able to decompose nearly all pesticides. And colleagues, that is exactly what we have. Here is the water contaminated with the methylene blue. This is its absorbance. After, when you mix a dark TiO2, black TiO2 in it, and you leave it for a certain moment, expose it to solar energy or not. So for the near infrared, after 30 minutes, you can see clearly that it is less blue dark, and therefore it becomes nearly transparent. That means the methylene blue was fully decomposed, colleagues. And that, what does it mean, colleagues? And here is the decomposition is there, and as you can see, initially it was blue, so that is the methylene blue, which is absorbing quite a lot. After 2 hours, you have this dark curve, which means the methane blue has been nearly absorbed, not 100%, but above 95%. And it is a way of using nano materials, engineered, bioengineered, but to very well geared towards defects, but not doping, to make them very active in the visible and the near infrared, and they are made using bio waste in effect. So all is mahala, all is cost effective and easy to be duplicated. And the other aspect also related to water, colleagues, you have noticed that Algeria now has embarked in a massive desalinization, such as in Kuwait and Qatar and so on. Except that one of the major problem of desalinization is, first of all, it's really energy intensive. If it is energy intensive, that means it is CO2, a very large CO2 or significant CO2 emitter. So in terms of CO2 footprint is high. The third is that the brine, when you remove the salts and all the, how can I say, the elements in that brine is not of use. It's stored. For the moment, there are no validated technology of using the brine. One of the technologies that has been embraced by quite a number of countries, specifically the UAE, you have noticed that last year there was a massive amount of rains in Oman and a massive amount of in the UAE, in Dubai in particular. Why? For the simple reason is that UAE uses a technology that we call cloud seeding for artificial rain harvesting. What is this cloud seeding? You have a plane, and that plane you fly over a cloud, and what you do, you inject in that cloud nanoparticles of silver iodide. Why silver iodide? Silver iodide has the same latest parameters, crystallographic parameters, as ice. Therefore, once these nanoparticles of silver iodide are in, what they do, the water which is under huge saturation, what they will do, it's a supercooled water or vapor water. So water, crystals of water will grow on these silver iodide crystals, and by doing as such, the droplet, the ice becomes heavy, big. They become big like a hell, and this hell, they are so large that by gravitation they move out of the cloud, and when they come out of the cloud, they come from a super saturated region to a normal region. And what happens is that this droplet, these large crystals, they melt, and when they melt, they give a birth to rain, and the rain, how can I say, is harvested artificially like this. In our case, colleagues, what I would like to share with you is that up to now they use crystals, large crystals, micron crystals of silver iodide, which is expensive now, which is expensive. While if you use nanoparticles of silver iodide, it will be cost effective. And here, the work that I would like to share with you was done by Shiva and myself, as well as Nagla from Sudan, and Shiva and myself from Iran and Pakistan, and Etani Madiba and Botumelo from South Africa and Botswana. Here, a typical case of, here is a pure water droplet, and here is a droplet loaded with silver iodide nanoparticles. And here is after a certain time, in a chamber where we simulate supersaturation conditions. As you can see, on the droplet with the loaded with the nanoparticles, you see clearly that the growth of crystals is larger than this. And I think it will be better if I can show you this movie. I will share with you this movie. Let me just go here, colleagues. This colleagues, here is the particle. The bottom one is the particle without which is not loaded with the nanoparticles, and the other one is loaded with the nanoparticles. So you can see the crystal growth of this ice grow easily on, and as you can see, it grows faster. We are in a regime of some minutes here, colleagues. So you see that you are growing the ice easily on the loaded water with the nanoparticles. Here, colleagues, again, for rain harvesting to address the water problem is a must. And I would like to, how can I say, maybe finish with this case here of smart windows, which is related to energy consumption. In our housing, in our houses, as in our cars, there is a huge heat loss or heat gain via the windows, glass windows. And to minimize this problem in the summer, we use the air conditioner and in the to cool. And by using the air conditioner both in the car or in a house unit, we do consume energy, and that energy is coming from somewhere. It's coming from a fuel, and that fuel, how can I say, we will produce that energy. To get it, we are producing CO2. Therefore, the idea is to develop a technology whereby we stop the heat coming from the sun when it's hot and allow the heat to come in when it's cold. And therefore, it both in windows in a normal house or in a car, because this is the thermograph of a house and this is of a car. You can see clearly the exchanges are mainly via the glass windows. Therefore, we have to come with a solution for the class for, how can I say, for glass windows. What we do, therefore, we have to come with a material that would coat the glass, and this coating, once it's put on a coated on a glass, it should stop the heat from the sun when it's hot outside, and it has to allow the heat to come in when it is cold outside. Therefore, when in the summer we want to stop the infrared radiations, and in the winter we need to have the infrared radiations coming in. So we have to have a smart material for such, and that's such the smart materials. These fellows who have worked on it, in addition to number of alumni from Cameroon, from Burkina Faso, from Ethiopia, as well as said Cameroon. Just not to go through the details, colleagues. Here is a smart a toy window house with the window without a coating, with a glass window without coating, but with a thermometer inside, shined by equivalent of 1.5 sun with this artificial sun. You can see, colleagues, that the temperature measured inside the room is around 42 degrees Celsius, while the house nearby it, with the window coated with that material, the temperature measured by the thermometer is around 33, nearly 10 degrees difference in between. So it shows you that this material here, this material is capable to stop the heat. Why? Because this material is an oxide which has a phase transition. It is metallic at a high temperature, and it is semiconductor at low temperature. What does it mean? Semiconductor allows the heat to the infrared to come in, but when it's metallic, it stops the infrared radiations. I will not go through the physics of it. The colleagues, please forgive me, time does not allow that. But what is sure, there is a intensive science in it. The point is, when it is hot, the window is blocking infrared. As you can see, the infrared is blocked. Here are the radiations in the infrared. The transmission is decreasing, while at low temperature, the transmission is higher. So that is a vanadium dioxide coating. You do understand that it would be used extensively in skyscrapers and building instead of using air conditioner unit. It's better to coat the windows with the, how can I say, with the smart coating instead. It will be, how can I say, green. It's energy not consuming, and it would not emit CO2, and you will not, the cost of cooling is by far extremely very low. The last case that I would like to share with you, which is related to fluid flow and when, if you depart from home, the engine of your car is cold. When you arrive at your working place or at your school, the engine is hot. If you put your hand on the engine, it's hot. Yet, from your home place to your working place, in effect, your engine was, the cooling system of your engine was operating. So the cold water was coming from the radiator, cooled by the fan and the system related, and it goes to the engine. It removes a certain amount of heat, which is generated due to the pistons. It comes out a little bit hot, and it goes back to another cycle. It's cooled, and it goes back again, and so on and so on. But the water that you are using is not capable to remove a huge amount of heat. Why is that? Because water has a limited thermoconductivity, and therefore, by its nature, it cannot have a higher, it has an intrinsic thermoconductivity, and therefore it will remove small amount of heat at each cycle. And therefore, by doing such, but by not being able to remove a large amount of heat at each cycle, the engine operates under heat stress, and therefore its lifetime is reduced, and the lifetime of the car is reduced. The amount of fuel that you are consuming is larger, and the amount of NOx and the CO2 that you are emitting is large. So it is necessary to use another coolant. Unfortunately, there are no other possibilities with the standard coolant. If you measure the thermoconductivity of the organic coolants and the heat transfer fluids that are used currently, all the thermoconductivity of these materials, all of them are spearheaded by water itself. The thermoconductivity of water is small. It's less than 1 watt per meter per Kelvin, while that of metals and oxides, the thermoconductivity is high. Well, the thermodynamic tells us if you could mix these materials in suspension in these coolants, the thermoconductivity is an additive compound, Therefore, you could expect that the thermoconductivity of a mixture of the composite will be a little bit above 1. So, in effect, colleagues, James Clerk Maxwell, the father of electromagnetism, in effect, he has not only written a treatise of electromagnetism, but treatise of thermal heat and thermal physics. And he was the first one who conceptualized the idea of a composite fluid. A composite fluid uh, consisting of a standard heat transfer fluid with the particles of a metal or oxides. That is what we call a composite fluid. And it happened that in his time they were not able to make it because they they were grinding these metals or their oxides, but when they grind they are at least micron size, maximum macron size, or sorry, minimum macron size. And therefore, when you mix them with the heat transfer fluid, gravitation makes it in a way that these particles, micron size, they will feed the gravitation and they will settle. But and that is why they have not succeeded in his time to make this new generation of composite fluids, cooling fluids. But currently, we are capable to make nanoparticles directly in the host fluid, being it water, ethylene glycol, or mineral oil. And because these nanoparticles are Brownian motion driven, they will feel less gravitation. And the Brownian motion will take it uh, uh, over the gravitation, and therefore the system can be stable for a number of days, a number of weeks, even months. I will escape this, how can I say, the theory of Maxwell in terms of nanofluid. So, sorry, let me just go back again. Because the nanoparticles are nano, so we call it a nanofluid. That's the term. And the nanofluids became a new generation of coolants. As you can see, colleagues, PhD student, a postdoc from Morocco, postdoc from South Africa, and a postdoc from Iran. This is modeling, this is chemistry, this is physics and material science. And I will escape these colleagues. Here is graphene sheets, and here silver nanoparticles. And also we made graphene sheets, graphene carpet covered with the silver nanoparticles. And as you can see, the thermal conductivity of ethylene glycol is there. It's around 0.32 watt per meter per Kelvin. When you go to silver in ethylene glycol, you have this. When you have to graphene alone in ethylene glycol, you have this. When you go to the carpet of graphene covered with the silver nanoparticles, you have such an enhancement here. And this enhancement is around 33%, which is massive. It's huge. Why we took silver and graphene? Graphene has the largest thermoconductivity of any compound. It's better than diamond even. Silver is the metal who has the highest thermoconductivity. That's why we combined both and we put it. And you would see that enhancing the thermoconductivity of a nanofluid relatively to, I can say, the same thing applies for water. You would understand that if you use it in an engine, it will remove at each cycle high amount of thermoconductivity of heat from the engine, and therefore the cycling is far better and the lifetime is. One of the application of the nanofluid which has seen it as moving fast new coolant is the cooling of photovoltaics. As you can see in this graph, photovoltaic, any increase of a 5 degree, an increase of 5 degree of of photovoltaic decreases its efficiency by 1%. Therefore, if you use water to cool it, there is no way that you will not lose in terms of uh, uh, in terms of rate of conversion. The red one is without cooling with the nanofluids, and here it's cooling with. So you can see, colleagues, that by cooling with the nanofluids photovoltaics, it will make, how can I say, the PV operating in optimal condition, in the correct conditions. And just following these different examples that I gave to you, colleagues, what happened is that the field of nanosciences and nanotechnology has allowed us more or less not to use publications or diplomas, production of diplomas as the compass or as the major metric, but also the translations of the research, taking it from technology readiness level 1 to technology readiness level 4, at least for the PhDs who would start, and if possible, once the technology is validated, it would allow to embark with the business sector and to take it to RL7 and therefore to the market. So again, the vision of the chair, I hope that within the examples that I shared with you, is that we are moving from level 1 to level 2 to level 3, and hopefully we'll go to level 4. And by that, colleagues, just to mention that in effect, the each year, the compound average growth rate of nanotechnology in the market is growing, and it is expected that from 2023 to 2028, it will be increasing by around a factor of 10%. So therefore, there is a possibilities for each of those who would like to embark in the field of nanosciences and nanotechnology. There is an opportunity of R&D translations and innovation. And by that, I thank you, colleagues. Shukran jazilan. Thanks a lot. And I'm done, Program Director. I do apologize if I took a lot of much of your time.
No, you
I
didn't.
do.
It was very fun. It was very fun and exciting. It was beneficial and insightful. Thank you, Professor Maza. Now, for the questions part, I will start with my own question actually. In the SDG of health, are we gonna start to see the solution that your friends got in the skin cancer in the pharmacies in the near future? Or is it still under development?
Well, thank you so much for indeed. What we do, remember, as I mentioned, we are dealing with our compass is the technology readiness levels. For our case, we ensuffle our aim is to ensuffle the notion of innovation within the spirit of our students. One. Two, when they reach, they finalize their PhD, they embark in a postdoc. And at the postdoc level, they have to produce a laboratory prototype. Once the laboratory prototype is finalized, then we have to go to the testings and so on, and toxicity, biocompatibility, that kind of stuff. As an institution, as a UNESCO chair, we cannot do it. So what we do a laboratory demonstration, a laboratory validation, and with a laboratory prototype, and therefore we publish we patent. First of all, we protect, then we approach those who are interested. But in our case, we don't go to the market. You do understand, we are not a business-oriented institution. What we do is that we try to find out if there is an interested third party, both in South Africa or out of the border of South Africa. Therefore, we impose to them that they should create a spin-off company, and that spin-off company should be led by one of the fellows who are among the innovators. And the students are involved in the patenting. So whenever there is a patent, the students are part of it.
Okay. Thank you, Professor. Now, anybody else who has a question?
All right, so hello, sir. Thank you so much for this amazing lecture. I just want to ask you, we all know that the SDGs were adopted universally on 2015, and the 183, I guess, member states agreed on achieving it by the end of 2030. So do you believe that nanosciences and nanotechnologies are gonna, make a big difference by the end of this 2030 in just 5 years? That's it. Thank you in advance.
Thank you so much indeed. Indeed, it's a really hot question in that regard. What is sure is that we are doomed to get it right. And the SDGs are also aligned, or other initiatives are aligned on SDGs. We take the African Union's TISA 2063. It's an extension of the SDGs. Maybe you are right that we will not fulfill all the SDGs as per expected in 5 years, but nonetheless, quite a number of them will be reached. Not all of them, but some of them will be reached in terms of final target. But what is sure is that it will continue. It will not stop. It will continue through a number of other initiatives and platforms. And specifically, I'm speaking about the African Union's TISA 2063, which incorporates within its policy and vision and mission all SDGs. You do understand, with the current instability in the world, with the wars everywhere, it's not possible to achieve it. We cannot hide the sun with the sieve. كما قالها الله يرحمه ورحمه الجميع بمدين الله يرحمه ما نغطوش الشمس بالغربال. We cannot achieve it if there were no conflict, yes, but we have a conflict in Ukraine, in Gaza, in X, Y, and Z and Z. So it is not possible to achieve it. So it will continue. Certainly, the United Nations would continue. The SDGs target will continue through other platforms. But we should not, we should not limit ourselves. We should continue targeting it. Why? For this, by the way, SDG 6, SDG 4 or 5, it's related to gender equity, isn't it? Correct me if I'm wrong. Colleagues, what I see here in this August auditorium, quite a large amount of female students. Correct me if I'm wrong. And this is one of the SDGs. And this is fantastic example that one of the SDGs is nearly to be achieved. The same thing in Rwanda. In Rwanda, the number of girls educated is far higher than in any African country or any country in the south and the north. But nonetheless, just seeing this August lecture theater where you are, the number of female fellows, mashallah, it's quite large. And that means that SDG 4 or 5 of gender equity is reached. Thank you.
Thank you so much, sir, for this conference. I really enjoyed the variety of applications of nanotechnology for solving human basic problems. My question is regarding skin cancer treatment, melanoma. How would you address the accumulation of metal oxide nanoparticles in the human body causing diverse conditions like Wilson's disease.
Again, this, how can I say, this type of studies, you do understand that we are material scientists and we are interested in engineering materials at the nanoscale. By training myself, I am a physicist, but nonetheless, I embarked in chemistry and biology and so on. I became multidisciplinary, not by luxury, but by necessity. So what we do is that whenever there is a problem, you mentioned the measles, what we do is that we meet the community who is interested by this aspect, and we interact with them and find out. They give us the problem, and we do our homework, literature review, using X, Y, and Z platforms to be able to find a potential solution. And what we do before embarking in any experiment, we use high performance computational capabilities to identify what is the ideal material, what is its ideal characteristics, and we embark in that regard. But the tests for the medical aspect, it's not us. We embark with in partnership with those who have that problem, and we try to find a solution together. What is sure is that I hope that in April I may come to Algeria, to Constantine, and I will jump definitely to your school to meet some of you and physically, and to find out if you have some specific projects. We will be ready to embark and how can I say and find out to get the solution. Thank you.
Assalamu alaikum. Well, thank you, sir, for this incredible conference that was filled with so many precious information. I would love to ask you one question. In your opinion, which one of the 17 SDGs is the most likely to be achieved with nanosciences and nanotechnology? Or are they equally have the same chance with nanoscience and nanotechnology? Thank you.
I think the energy one, SDG 7. SDG 7, because the pressure worldwide would make it in a way that SDG 7 would be the one to be targeted. Why? Because SDG 7 is the one who is behind the climate change, the CO2 emissions. So because the CO2 market will come in force normally by 2028, all countries will be geared towards minimizing the CO2 footprint, and therefore they will put the government, public, private sector will put a huge amount of efforts to minimize the CO2 footprint. Therefore, they will try to go for the SDG 7. So it's there where the efforts will be made extensively. And if you have a clean energy, you will be able to desalinize water easily. You can have hospitals which operate with a minute amount of CO2 footprint and so on. Just to remind ourselves that Algeria is the second major polluter, major emitter of CO2 in Africa. The first one is occupied by South Africa, which is number one in terms of emission. It's 7.4 metric tons CO2 per person per year. And Algeria, it's a little bit smaller. But any country, all countries will be obliged to embark in the SDG 7. Thank you.
Thank you so much.
Hello, sir. I want to thank you again for your amazing explanation. I was quite impressed by how much of this application have already taken place. Sorry. I want to ask actually, you mentioned that all of those nanotechnologies and all are quite expensive, and we already know that many of them are under experiment. So, how would it be possible to have them in real life? I mean, it's quite expensive to produce them. So how can we get a big amount of those products to help out with other problems? And thank you in advance.
Thank you. Thank you so much. In effect, as I have mentioned at the beginning, the field of nanotechnology is a potential field whereby we can produce excellence in terms of research and excellence in terms of education, but also I have mentioned it, to implement a laboratory in the field of nano does not require huge amount of investment initially if we target exactly what can be achieved. For example, uh, one of the hot topics one of the hot topics is green nanochemistry. It's a green biophysical chemistry. Here, you use natural extract as a very effective chelating agent to produce a massive amount of materials. And also, how can I say, you can use basic laser source to generate an outstanding amount of nanomaterials with an outstanding amount of properties. For example, CDTA, I have no clue how far CDTA is from your institution, but we could, how can I say, you could interact with this institution who have this average cost facilities to produce materials of a high value. So it is possible to implement nano research projects with extremely minute costs, but with a high impact.
Professor Maaza, assalamu alaikum. I'm Professor Mahmoudi. I thank you for your time. We know that today's weekend and you are with us. Thank you again. Thank you again for the excellent presentation and to give this talk to our students. I guess they learned a lot today. I invite you, of course, to come to our school in next April and maybe give a lecture in physical directly and meet with our students. They are much more interesting in physical contact than the with the webinar. I also invite you to join our scientific council of the school. It may give us strong ideas when discussing the future of our school. Also, we would like to be involved with you in the UNESCO chair to take advantage of what you are offering to the different African countries. And I hope when you will come to our school, we will discuss deeply in the different opportunities of collaboration. Once again, thank you very much for your time and for the excellent keynote you gave. Thank you.
Thank you so much, shukran jazilan, and I certainly look for visiting you physically and explore possibilities of student exchange and senior fellows, and we will look also for possibilities of joint funding to equip your institution with the different laboratories in the field of nanosciences and nanotechnology. Shukran jazilan. Assalamu alaikum.